Hello, my name is Krzysztof Rzadca. I work as a visiting researcher at Google Warsaw and as an associate professor at University of Warsaw, Poland. I'm going to present Autopilot, a tool we developed to automatically scale the workloads in Google internal cloud. In our internal cloud, a job can serve YouTube or Gmail to millions of end users. Or it could be a batch computation, recalculating database indices. No matter what is the job type, to launch it, we pack it in a container. Key feature of the shipping container is the metal box that surrounds the payload. This metal box protects the payload from the outside, among others, from the payloads of other containers. Similarly, a Linux container isolates workloads by setting limits on the maximal amount of resources processes running in the container can request. The actual usage is usually much lower. What is left is slack, memory or CPU that is allocated but idle. Borg, our scheduler, uses container limits to pack containers onto machines. For high priority serving jobs, Borg makes sure that there are sufficient resources on the machine to fulfill all requested capacity. Limits are fine-grained. You can request computational powers in unit of millicores and memory in single bytes. As you can see, our internal users actually make use of this fine granularity. If we rounded up the limits to the nearest nice-looking value, such as 1, 2, 4, or 8 cores, we would need much more resources in our fleet. However, for humans, it is very hard to accurately set these limits. This presentation is a job running in a cloud. How much bytes of memory a container running it really needs? So, as with shipping containers, you have to pack your machines by the size of the external box, the limit, and not the actual payload. What you see here is a machine that executes 3 containers. The limits are just about right, slightly higher than the actual usage of the containers. There are 2 kinds of problems with imprecise limits. First, limits can be set too conservatively. Jobs are safe, but the resources are wasted. The machine cannot accommodate another container, yet the actual utilization of the machine is really low. On the other hand, if we set the resource limits too aggressively, as on the right, a container could request more resources than available. If this is memory, such a container will be killed with an out-of-memory error. Autopilot is a tool to automatically set the limits and the number of containers the job is executing. Autopilot is a controller working in a feedback loop. Autopilot recommenders compute resource limits for a job. These limits are forwarded to Borg, our scheduler, which then contacts individual schedulers on machines. These schedulers are called Borglets. Borglets, in turn, set Linux cgroup limits, or they start and stop some tasks. We continuously monitor usage of resources of each container, and this resource usage log is then read by recommenders in a feedback loop. So, Autopilot recommenders are responsible for calculating resource limits. They are the key logic of Autopilot. And we will describe 2 main types of recommenders. The moving window recommender uses simple time series methods to calculate limits based on the usage signal. We calculate statistics of the usage falling in a moving window. Statistics such as the 98th percentile. We then smooth the response by exponentially decaying the input. Finally, we add a safety margin. This simple mechanism is sufficient to show significant savings. However, different categories of jobs require different tuning of the safety margin and the decay rate. For instance, a job with unstable usage requires more smoothing than a stable job. Our machine learning recommenders use ideas from reinforcement learning to automatically tune the parameters of a the moving window algorithm. Internally, a machine learning recommender runs many individual so-called models, and each model is a moving window algorithm parameterized by different value of a safety margin and a different decay rate. Each model picks a limit according to its parameters and the moving window algorithm. Then the machine learning recommender chooses the model to write the future recommendations based on each model's historical performance. To evaluate Autopilot performance, we conducted an observational study of production jobs running in our internal cloud. We focus here on memory, as out-of-memory errors are harder to cope with than just CPU throttling. To measure the efficiency, we measured slack. The absolute slack is the difference between the total limit of a container and the total usage. Both totals are summed over a day. So the absolute slack of 0 translates to the limit always exactly equal to the usage, a very ambitious target. The relative slack is the fraction of allocated but unused resources. Here, we use the 95th percentile over a day to express the daily average. To measure so autopiloted jobs have significantly smaller slack. The average relative slack is just 23%, compared with 46% for manually managed jobs. Additionally, you can see that the ML recommender has even lower slack than the moving window recommender. For the absolute slack, we measured the slack of the 5,000 jobs in each category. The total absolute slack of 10,000 autopiloted jobs is the amount of memory of over 12,000 large machines. On the other hand, the autopiloted jobs have the absolute slack equal to just 500 machines. When jobs migrate to autopilot, their slack is significantly reduced. We observed a random sample of 500 jobs that migrated to autopilot in a certain month, called here M0. Before the migration, the average relative slack of these jobs was 75%. The migration reduced the slack to just 20%. The reduction in absolute slack was similar. To measure reliability, we measured how frequent the out-of-memory errors are. We weighted the number of container terminations due to out-of-memory errors by the number of containers in a job. The idea is that a job with many containers is less affected by a kill of a single container than a job that has just a handful of containers. We found out that first, out-of-memory errors are rare. For autopiloted jobs, 99.5% of job days don't have any out-of-memory errors. Additionally, autopilot has smaller slack, but also actually less out-of-memory errors than manually managed jobs. In our paper, we additionally show that autopilot has a smaller number of serious out-of-memory errors. By serious we classify an that affects too many containers of a single job. Currently, autopiloted jobs account for over 48% of Google's fleet-wide resource usage. And autopilot's dynamic limit setting could help to mitigate the impact of bugs. This is a screenshot from our monitoring system showing execution log of a single job that was manually managed. Autopilot is running in a dry run mode. It computes recommendations, but they are not actuated. On the left, you see that a new version of a job had a memory leak, causing the memory usage to steadily increase. Autopilot would detect the leak and increase the limit in 3 steps. However, the job was manually managed. Individual containers started to hit the limit and then be killed. And this, in fact, affected the end user performance. The on-call DevOps engineers started to work on the problem, yet it took almost 2 hours to roll back the binary to the previous version and restore the service. Autopilot would give the DevOps engineers more time to find and correct the memory problem. To summarize, Autopilot shows the gain from automating cloud resource management. Humans are bad at setting the limits precisely. With Autopilot, our fleet runs more efficiently. The relative slack is reduced by a factor of 2. Additionally, as we show in the paper, this reduction is almost for free. The risk of out-of-memory errors for individual jobs actually decreases compared to manually managed jobs. Thank you very much.